Hello everyone, my name is Kalanie Wilson. I am a dual degree student pursuing a Bachelor of Science in Chemistry from the University of North Georgia and a Bachelor of Science in Chemical and Biomolecular Engineering from the Georgia Institute of Technology, where I'm currently studying at. I would like to thank everyone for joining in for my final presentation on high entropy alloys as biomaterials for potential use in the human body as implant materials. So what are biomaterials and biomaterial implants? Biomaterial implants are made up of biomaterials which have a broad range of applications as depicted on the right. Biomaterial implants are typically used medically and are placed in the body with a goal to help restore patients back to a normal quality of life. But not just any element is classified as a biomaterial. A biomaterial must be biocompatible, which means it cannot cause any adverse responses to the body. If there is not certain selectivity considered when making biomedical applications, then corrosion will eventually occur and lead to deterioration, which causes the implant to fail. And due to the selectiveness of biomaterials, there are a limited amount of materials that can be used for biomedical applications. This led to the creation of HEAs, which are composed of 5 or more elements and possess superior properties compared to conventional alloys. In the pictures to the right, we can see what happens when multiple elements are used. We have an irregular shape. This is explained by the core effects. There are 4 core effects governing the thermodynamics, kinetics, properties, and structures of the HEAs. The high entropy effect details that since HEAs have a higher mixing entropy, this causes the energy of the solution to lower at higher temperatures and causes a single solid phase to be stabilized. The cocktail effect describes the properties of HEAs related to its composing elements. For example, adding lighter elements decreases the density. The properties are also defined by the interactions between the component elements. For instance, aluminum is soft and has a low melting point, but if it is added to an HEA, it can harden the HEA. So the sluggish diffusion effect proposes that the diffusion of HEAs are slower than conventional alloys. What happens is in HEAs, the neighboring atoms of each lattice site are different, as seen on the picture. Thus, the neighborings before and after an atom jumping into a vacancy is different. The difference in local atomic configuration leads to different bonding and therefore different local energies for each site. When an atom jumps into a low energy site, it becomes trapped, and the chance to jump out of that site will be lower. In contrast, if the site is high energy, then the atom has a higher chance to hop back into its original site. Either of these scenarios slows down the diffusion process, whereas in conventional alloys, the configuration before and after jumping into a vacancy is mostly identical. Additionally, the diffusion of each element composing the HEA is different. Some are less active than others, causing elements to have lower success rates for jumping into vacancies. Lastly, the severe lattice distortion describes the distortion of the lattice due to the composing elements being different sizes. The top of the picture shows a perfect lattice with the same atoms. The bottom picture shows a distorted lattice with solid solutions of different sized atoms. The larger atoms push away their neighbors, and small ones have extra space around them. This results in distortion, and there are 3 defined types of classifications for the lattice distortion as shown. This research intends to determine possible alloy combinations that can be more compatible, stable, and corrosion resistant in the human body than the traditional implant materials. The use of biocompatibility alloys will solve the problems associated with having long-term implantation due to the exceptional mechanical properties they possess, as well as corrosion resistance. We aim to do this by analyzing and predicting a better alloy both experimentally and computationally. For this project, my focus will be on the computation, and I will be using the OLI Studio Corrosion Analyzer to test multiple solutions with different alloys used in biomedical applications. The predicted corrosion rates, stability, precipitation formation of all the different alloy and solution combinations will be evaluated. The solution and/or alloys that seem to possess good potential can be observed and analyzed further experimentally in a lab setting. Experimentally and computationally, a simulated body fluid, SBF for short, is created to mimic an environment close to that inside of a human body. A contact surface of choice, or alloy, will be put into contact with the SBF to see what interactions take place, what precipitates might form, and what solution parameters change, if any. The goal is to maintain a pH and ion composition relative to the one in the SBF, so one similar to a human body, as well as have no harmful interactions that could damage the human body. Additionally, the type of precipitates that form and are present influence the corrosion behavior. These areas of importance will help to identify what materials have potential for practical applications, as well as gain a better understanding of what phases are formed and how that affects the HEA. Using the OOI software, the SBF can be created by inputting the mass of each component used into the inflows table. Looking at the picture below, on the left you can add your components to the inflow table, and on the right you can enter the amounts of each substance. After creating the SBF, a single point isothermal calculation will be performed to view a calculation summary report of the solution. The report generates various information, but the areas of interest include the stream parameters, scaling tendencies, and the species output. In the stream parameters, we are interested in the aqueous properties, and we need to maintain the determined pH, one close to the human body. The scaling tendencies provide a list of predicted solid precipitates to be formed on a scale from 0 to 1 meaning a solid formed. The goal is to maintain carbonate hydroxapate as a solid precipitate, so a scaling value of 1 and all other precipitates at a minimum. Carbonate hydroxapate is the solid precipitate of interest given it will most resemble the formation of human bone. The species output provides the total aqueous and solid molar concentration of each ion in the solution. The goal here is to have 0 solid molar concentrations. In red, we see the chloride ion concentration highlighted. For a greater understanding of the created SBF, the mass of certain components in the SBF were altered with the desire of this chloride ion concentration, in red, to be 10 times more and 10 times less than the original chloride ion concentration. So what we did was take the previous chloride ion concentration we saw highlighted in red and multiplied by 10 and divided it by 10 to give us the goal in mind of what chloride concentration we are looking for. And we found that the components that we can alter the most without changing the pH of the solution, so keeping it around the pH of the body, or forming a different precipitate than the one desired by changing sodium chloride and potassium chloride in the software to see when we have reached our goal of our chloride concentration that is 10 times more or 10 times less of the original chloride concentration, the mass of the NaCl and KCl were manually changed in the inflows parameters, which is highlighted in the red box. And each time the mass of the component is changed, the calculation in OLI has to be preformed again to generate a new report, and the chloride ion concentration has to be rechecked. Once the desired chloride ion concentration is found, the corresponding new inflows for each component will be tested in the lab. Not only can the OLI software be used to predict results from the SBF solution by itself, but it can also be used to introduce a contact surface to the solution. By introducing a contact surface, a stability graph can be generated and corrosion rates can be calculated. The stability diagram is a representation of the Borax diagram, which shows the possible thermodynamic stable species of an aqueous solution at different potentials in pH. One key observation in the diagram is the oxidation redox potential, ORP, which is indicated by the thick red box on the diagram. This value can be compared to the corrosion potential to determine if corrosion will occur. The table on the slide lists all the possible alloy combinations that can be used in OLI for corrosion calculations. The composition of each element making up each alloy is listed. Using this information, we can determine which alloys in OLI can be used to make calculations that closely match the alloy used in the lab, as well as have a similar composition to conventional alloys. The alloys selected to use in OLI were alloy 29 and stainless steel 316. It is also important to note that the corrosion rate plot for each alloy available in OLI was generated and viewed to see if any pitting will occur. For alloy 29, no pitting was observed, but for stainless steel 316, there is significant pitting corrosion. Here we can see the corrosion rate plot for alloy 29 by surveying temperature as well as pH. Next, we see the corrosion rate plots for stainless steel 316. Already you can tell a difference when compared to the alloy 29 plots. We see a blue line in the plots. The blue line represents the pitting corrosion that will occur. Any amount of pitting observed will end up compromising the implant. Here we have the data that was used to generate the plots on the previous slide. In OLI, the corrosion rate data is in millimeters per year, which for a biomedical application standpoint, it does not provide any insight. Thus, using some unit conversions and the density of the alloy, the corrosion rates can be converted into milligrams of metal per year. From here, we can see how much metal is leaching out into the human body each year. But we can take it one step further and see how much of each element making up the alloy is leaching out into the body per year. To do so, we can take the desired element's composition and multiply it by the total amount of metal leaching out into the body per year. For example, in alloy 29, the nickel composition is 29%. So if we multiply the corrosion rate in milligrams per year by 0.29, you will have how much nickel is leaching out into the body per year. The corrosion rates for both elements, nickel and chromium, were calculated since these two elements are the most harmful to the human body. Previously, we selected alloy 29 and stainless steel 316 to be used to make corrosion rate calculations since these two alloys are similar to the alloys used in lab as well as literature. So to take it one step further, we can also analyze the same alloys from a thermodynamic standpoint by generating a stability diagram. The only restriction is in OOLI, it does not offer alloy 29 as an option to select in order to generate a stability diagram. Thus, we will just be looking at the one for stainless steel 316, which is seen on the slide. Here's the overall stability diagram for 316, and the colors represent what type of corrosion might take place. The cream color represents corrosion, green means passivation, which it will perform a protective layer, and the gray shows the electrolyte exposure. In the red box, this is where we would expect most corrosion potentials to fall given the pH of the human body, which would correspond to the passivation, so a protective layer will be formed. If we go one step further and generate a stability graph for each element, then it will provide more information about what is actually happening. Here is the stability diagram for iron. We see that it's entirely cream, which leads us to conclude that the iron is dissolving into the solution and the chromium and nickel are forming the protective layer. Now to bring the kinetics and thermodynamics together. We can take the generated corrosion rate data and determine where those values for each pH will fall on the stability diagram. On the left, we see the corrosion potentials from OOLI with its corresponding graph color and interpretation from the stability diagram. The ones highlighted in yellow is where we would expect to see values in the human body given its pH value. In the table on the right, we see confirmation that the potentials do fall where we expected, and we will form a passive layer. The next steps include comparing the results from the OOLI software to the experimental results for the new SBF solutions with higher and lower chloride concentration. Also, further compare the corrosion rate data and stability diagram generated from OOLI to those experimentally. The OOLI software will also be used to test more alloy combinations used in biomedical applications and start to observe any effects or changes that the concentration of the SBF solution might have on the corrosion rate data. Additionally, trace how many years an implant can be in a body before the toxicity limits of nickel or chromium is met. I would like to say a huge thank you to all of my support, my mentors, Dr. Case and Dr. Castaneda, my lab partner, Nina Castaneda, and my other corrosion team members, Karen and Ramon, the National Corrosion and Materials Reliability Laboratory for allowing me to be part of their team this summer, and the Texas A&M University ORU program for giving me this opportunity, and Creeds for helping fund the program, and these are my references. Thank you.